Good morning. This is Chapter 4, Section 3, Newton's second and third laws of motion. Quick reminder, we are currently at December 2nd, so we're going to finish up 4.3. Tomorrow we're going to do 4.4. Thursday, Friday, and Monday we're going to continue 4.4. Next Tuesday and Wednesday will be review days, and Thursday and Friday will be the Chapter 4 test. A will be on December 11th, and B will be on December 12th. The learning targets for this activity, or these notes, are: I can identify and explain the acceleration of an object in terms of its mass and net external force acting on it. I can predict the direction and magnitude of the acceleration caused by a known net force, and I can finally explain and identify action-reaction pairs. Tomorrow, or the next period when you have this class, we will be doing Chapter 4.3 quiz. Chapter 4.2 review is part of these notes, and then we'll finish up with Newton's second and third laws of motion. Homework assignment is reading Chapter 4, Section 4 in your textbook, watching the notes for Chapter 4.4, taking the practice quiz, which are both posted on my website on Sophia. Newton's laws of motion. First law of motion: an object at rest will stay at rest. An object in motion will stay in motion at constant velocity unless acted upon by an unbalanced force. Newton's second law is simply an equation: force equals mass times acceleration. And Newton's third law of motion: for every action, there is an equal and opposite reaction. Quick reminder, Newton's first law, and you, don't let this be you. Make sure you're wearing seatbelts. Because of inertia, objects, including you, resist changes in their motion. With a car going 80 kilometers per hour is stopped by a brick wall, your body keeps moving at 80 kilometers per hour. Newton's second law of motion is simply an equation. Force is equal to mass times acceleration. Mass is in kilograms, and acceleration is meters per second squared, which means that force is measured in newtons. The net force of an object is equal to the product of its mass and acceleration, or F is equal to ma. A quick reminder, 1 Newton is equal to the force required to accelerate 1 kilogram of mass at 1 meter per second, or 1 kilogram meters per second squared. Sample problem. How much force is needed to accelerate 1,400 kilogram car 2 meters per second squared? Your givens are the mass of the car at 1,400 kilograms. Your acceleration is 2 meters per second squared. The unknown is force, and so you simply use the equation force is mass times acceleration, plug in the numbers, and you end up with 2,800 newtons. Newton's second law proves that different masses accelerate to the Earth at the same rate, but with different forces. You'll notice that both the 10 kilogram object and the 1 kilogram object both accelerate at 9.8 meters per second squared. The difference is that the force that hit the ground is different. Force is equal to 98 newtons for the heavier object and 9.8 newtons for the lighter object. What acceleration will result when a 12 Newton force applied to a 3 kilogram object? The correct answer would be 4 meters per second squared. The net force of 16 newtons causes a mass to accelerate at a rate of 5 meters per second squared. Determine the mass. The correct answer would be 3.2 kilograms. How much force is needed to accelerate a 66 kilogram skier at 1 meter per second? 66 newtons. And what is the force of a 1,000 kilogram elevator that is falling freely at 9.8 meters per second? 9,800 newtons. Newton's third law of motion states that for every action there is an equal and opposite reaction. According to Newton, whenever object A and object B interact with each other, they exert forces on each other. When you sit in your chair, your body exerts a downward force on the chair, and the chair exerts an upward force on your body. There are two forces resulting from this interaction, a force on the chair and a force on your body. These two forces are called action and reaction forces. Newton's third law of motion in nature. Looking at the fish, a fish uses its fins to push water backwards. In turn, water reacts by pushing the fish forwards, propelling it through the water. The size of the force on the water equals the size of the force on the fish. The direction of the force on the water backwards is opposite to the direction of the force on the fish forwards. Another example of Newton's third law in nature is a bird flying. In this case, the size of the force on the air equals the size of the force on the bird. The direction of the force in the air downwards is opposite the direction of the force on the birds upwards. This pair make it possible for birds to fly. Another example, the baseball forces the bat to the left, an action. The bat forces the ball to the right, the reaction. And another example, consider the motion of a car on the way to school. A car is equipped with wheels which spin backwards. As the wheels spin backwards, they grip the road and push the road forward. In one final example, the reaction of a rocket is another example of Newton's third law of motion. Various fuels are burned in the engine, producing hot gases. The hot gases push against the inside tube of the rocket and are expelled out the bottom of the tube. As the gases move downward, the rocket moves in the opposite direction or up. Your homework: read Chapter 4, Section 4 in your textbook. Watch the notes for Chapter 4.4 and take the practice quiz. They're both posted on my website on Sophia.